media. I am Jesus Arturo Pérez. I'm a professor of the Guadalajara campus of the Tecnológico de Monterrey. I will be presenting a paper called a hybrid model for BGP anomaly detection using median absolute deviation and machine learning. This was done in collaboration between the Tecnológico de Monterrey and LACNIC that supported us along our research work. The contents of my presentation will cover the following. I will be making a brief introduction to the problem we are dealing with. We'll make a literature review, the objectives of this research, the research design and experimentation, the results, the discussion, contributions yielded by this research. As you are aware, BGP is crucial for the proper functioning of the internet. It is in charge of the routing information exchange. We can classify these anomalies in 4 different types, depending on the classification that Musawi used in a publication. So we classify the BGP anomalies in 4 major groups. The first group could be the direct intended anomalies. This is when someone intends to attack the BGP functioning. Then we have the direct unintended anomalies, where we could include misconfigurations. We then have the indirect ones. These are the anomalies that occur in BGP, for example, when we are under an attack. And then we have the link failures, which these normally would occur, for example, when there is a power outage or lack of power in some specific places. We are agree when there is a problem with BGP, this could have several types of impact. It could be an economic impact. It can affect e-commerce platforms, social media, and a good example is what occurred with Meta back in October 2021, when the Facebook, Instagram, and WhatsApp platforms crashed for 1 day as a result of a BGP misconfiguration. Then we also have this could also affect services, critical services, such as emergency services, healthcare, and quite obviously, everything related to privacy and data security, which is the other major problem that we might have. For example, data security and privacy, particularly when we have a route hijack. So when we analyzed these anomalies, we decided to focus on those that had been studied least. We reviewed the current literature, and we saw that the direct intentional anomalies on BGP were those that had been researched most. And as we see from this table, we decided to identify those anomalies that were least studied. For example, the direct unintentional anomalies, the indirect anomalies, and those that have to do with link failures. We proposed creating a hybrid model, as we will explain in a while. This table, in addition to reporting the main motivation of our work, also reports the performance we obtained, and as you can see, this had a better performance.
So the key objective of our research was to create a hybrid model that would, on one hand, consider statistical analysis, and this would be of use because we would be able to detect attacks never seen before. So in order for me to train a machine learning or deep learning or AI model, we need the attacks to be existing attacks with a history so that I can feed the model. But we wanted to detect some anomaly that had been missed, but that existed. And that is why we decided to integrate a statistic component. But on the other hand, we also tried to integrate the AI component so as to later on improve the model. Our key objective was to create a hybrid model containing the two parts. So, the first thing that we did was defining what we would consider an anomaly. So we conducted an in-depth analysis of the characteristics or the fields that were affected of BGP when this type of anomalies happened. So we chose that when the number of announcements and withdrawals were substantially increased for more than 6 minutes, then we would be able to state that anomaly was taking place. And basically, that was our definition for anomaly. As you can see at the bottom, to your left, for instance, you have an anomalous data. You have an anomaly that happen when there is an anomaly, and on the other, you have normal traffic where you see peaks, but they are not sustained. For us, the source of information that we obtained for this study, we downloaded data of RIPE, basically into routers that concentrated BGP traffic. We used the one in Switzerland, in the RISO IP European Network Coordination Center, and then the one in the Netherlands. And we used them to feed both the machine learning models and our previous statistical analysis. What data did we extract? What did we use for this research? So, as I told you, something that we wanted to study the other anomalies that had not been so analyzed. So we worked with 3 indirect anomalies caused by attacks, past attacks, including Code Red, Slammer, and Nimda. Those were 3 terrible worms in the early 2000s. Then we had the link failure that was a blackout, and finally a direct unintended anomaly such as TMNet. Because of a misconfiguration. So, in order for us to process the data after extracting them, what we did was to use the BGP stream library, the API. So we extracted the data in those dates. They're on the tables, paying the anomalous events, and then we took this information from RIPE's databases. Now, the first approach was, as I said, trying to find a statistical model that would enable us to detect when anomaly with a BGP anomaly was taking place. So, to that end, we defined this formula. And basically, the idea was to find the so-called median absolute deviation, and this was equivalent to taking the absolute value of the median of all the values of data of the dataset with respect to those parameters. Now, when when the median absolute deviation was higher than n, when n was the threshold for each anomaly, and it was sustained for more than 6 minutes, then our system would activate and say that there was an anomaly. We conducted some tests. For instance, here you can see the way would we visualize code red, for instance. And then here you see an increase. In green, you see the occurrence of the anomalous event, and we have the number of announcements and withdrawals that increase during the occurrence. And in the next slide, we already have an overlay. In brown, you have the MAD detection. So you see that the system, our system, could detect most of the occurrence. There was a small part that went undetected. However, it detected the anomaly. And if we see the statistics, well, we work with the most common metrics that are used for detecting these systems, including the true positives, true negatives, and the false positives and false negatives. And stemming from this, the most conventional metrics that have to do with accuracy, precision, and the value of F1 score that are typically defined by these formulas, where basically we seek weighing the true positives or the values that were effectively calculated as a true occurrence, and also those that were effectively calculated or were properly predicted when it was not an anomaly. So, based on these formulas, well, we proceeded to draw results. And as you can see, usually the accuracy values were quite acceptable. Precision was even better. Accuracy and F1 score, well, there were things that there was room for improvement there. So we decided that we would incorporate a threshold or an N value different for each kind of anomaly, because something that we discovered was that that value that had been obtained empirically after some tests, we saw that for some types of anomalies, a specific threshold was more favorable. So we calculated the proper threshold for each of the most common anomalies that we were studying. So that threshold value was fit for each of the anomalies, going from 1 to 5, and then with calculations that I detailed in the previous slide. And basically, the idea was to find a combined score that was 0.6 of F1 score and 0.4 of the precision, so that the thresholds would vary. With these dynamic and thresholds optimized for each anomaly, we run our statistical model once again, and as you can see there, we improved performance quite a lot, especially it improved with the dynamic threshold. The F score improved, and the accuracy and precision values also improved slightly. For instance, in the case of Slammer, we got a perfect precision and an accuracy of 0.95%. After this improvement, well, we are happy with the results of the algorithm. The advantage of this first stage of our research was precisely that without getting much computer power as demanded by the AI models, we would be able to detect anomalies. So we proceeded to improve the model by making it hybrid with AI. And here, just to conclude, the MAD model, to your left you see the original traffic, and afterwards you see, after improving the dynamic threshold, that we detected much more. And in the curve you see clearly that the results are better. So to incorporate AI, we had to integrate more features. So we conducted literature research to see the statistics that could have a greater impact in BGP anomaly detections. And we found that, as you're all aware, the AS path that defines the route of all of the autonomous systems through which a packet goes to reach destination is a very important characteristic, so much so that we integrate the length of the AS path, the maximum AS path length, and the standard deviation of the AS path length as three characteristics additional to the number of analysis and withdrawals, and the number of duplicate withdrawals, and the number of unique withdrawn prefixes. So, with all these characteristics, we started training a number of models. And to train these models, we had to create two data sets. One of them was created with the traffic labeled by MAD, and the other was the data set, the raw data set, just as we had downloaded it from RIPE. So we were creating two data sets for the purpose of training of to train our models to see which one had better results. And here you see on top we labeled the anomalies with 1 using our hybrid, our MAD algorithm, and at the bottom we used it just by labeling them based on occurrence. So we started training many machine learning models that are here: Random Forest, XGBoost, CatBoost, LightGBM, and Extra Trees. And as you can see, we were quite happy to see that with MAD, or the dataset that we created with MAD, we obtained better results in terms of precision. And most parameters were better in terms of recall, accuracy, and F1 score. We achieved quite high accuracies, which is telling us that in the hybrid model, when you combine this statistical algorithm with machine learning techniques, you can increase the accuracy level. Here we'll see the same comparison that we saw in the table, but graphically. Here you can appreciate that, well, the blue bar, those are the results obtained from our models based on occurrence, and the orange bars are the accuracy and F1 score results with the data set labeled with our MAD system. And so here in this image you can see what happens when we overlay the results of the anomalies. To your right, highlighted at right, is the part detected of the anomaly and overlaid on occurrence. So when we use the hybrid model, we see that we cover almost the entire occurrence. But this leads us to an even more interesting analysis, because it's very likely, remember that we are detecting BGP anomalies, not necessarily attacks. Anomalies that were caused very often because of indirect situations. So we might conclude, among the things that we debate in our publications, that probably the spaces that are not detected by our hybrid model, it's actually because there was no anomaly in the BGP traffic. It was just the period that was published as a duration of occurrence, for instance, when there was a worm attack. And finally, I wanted to tell you that the results of this research were published in two articles.
One is a journal that has a high impact, and the other is a YouTube journal. And as a result, as I mentioned before, we created a hybrid design that potentially allows us to detect attacks or anomalies in BGP on day 0, which were not seen previously as a result of a statistics model, and then a very precise system with a very high accuracy. When we combine the results of the hybrid model for potential attacks that could have been previously generated. Likewise, we are considering to make a study of the anomalies, for example, those that we haven't studied so far, which are those that are directly intentional anomalies, as would be route hijackings. This is among the future studies that we wish to carry out. We also proved that the integration of machine learning models does contribute to improve what we can do with statistical analysis. Finally, I would like to especially express my thanks to Carlos Martinez from LACNIC, who supported us throughout this research. And also, I'd like to thank Alicia Sujete and Laura and the entire LACNIC team who helped us, including funding, to carry out this study, and of course, the entire team for their ongoing support. Thank you very much. Are there any questions? We have time just for one question. If there are no questions, let us thank you very much.